Okay, so let's start this last lecture. It's a bit. What about now? Is it fine? Yeah. Okay, so let's start this last lecture. It's also on self-supervised learning. The other day we had a lecture on self-supervised learning from video frames, and now we are going a bit beyond, as we are going to take video not as only as a multimedia document for visual features, but also for audio features, because in video there are also audio tracks, and that's also an interesting signal that we can exploit for different applications. So basically the main motivation is that I know that you are in a Master in Computer Vision program, but there are some people out there who are doing Master in Computer Vision, Masters in speech or music or audio technologies, right? And all these people, we have found like some ring to rule us all, or some things to rule us all, like which we like the perceptrons, right? So all these people, they are also using neural networks to solve their task, and that's very exciting because it gives us a common language that from which we can exchange and learn a lot and develop new exciting tasks. So the basic idea that I will follow like through all the lecture is that so we have seen that with neural networks, one way to understand what they are doing is that these are models that they learn representations from our data. If you have an image, you can think that when we are solving image classification, in the end what we are doing is we are predicting a one-hot encoding, in which we expect that like the highest class, it's the one that corresponds to the right label, and it's kind of a representation as well, just that it's a one-hot encoding, right? And so we can go from one image to these representations, and we can think that these representations as locations in a high-dimensional space. In this case, we would like 3-dimensional if there was a classification problem with only 3 classes, but we know that we may have many more, which is just a higher dimensional space. For example, in ImageNet, you can think like that solving ImageNet, it's equivalent to projecting our images into a high-dimensional space of 1,000 dimensions, because there are 1,000 classes in ImageNet. It's the same problem, but you can think about it from another perspective. So we go from images to representations, okay? And what's interesting, as speech and audio people, they are also using neural networks. They can also do the same thing. They can go from their signals to some kind of representation, and that gives a common features. That can lead us to common feature space from which we can develop interesting applications. More interestingly, also we can also go from one of the representations to, in our case, to pixel space, right? So you had lecture with Michał, I guess, on generative models, or Adriana, Michał, yeah, in which so given a label, for example, of an object, that would be that would provide enough data to generate images. So based on this perspective, and also the speech people, audio people, they also have different things. I'm going to follow this approach. Like we have images or videos, actually videos. We have audio signals, and we know both how to encode it and decode them with neural networks. And if we can do all of this, there are many opportunities ahead for new applications. So in particular, this lecture will focus in the case we'll focus in trying to exploit that in the case of videos, considered as multimedia document. There's both visual and audio information which is synchronized, and it kind of comes synchronized for free, right? So whenever you record a video, you are capturing the light, but you're also capturing the sound waves, and they are already synchronized. And this synchronization might be enough to develop a self-supervised learning task. So as I know that you have followed the problem of Master in Computer Vision, this is probably going to be the first time you think about what about audio? How do you deal with audio? So for many of you, that's going to be the first step. But good news is that you probably know everything you need to know to deal with audio nowadays in deep learning. So how can we encode or decode audio? So to encode it, surprise, you can use recurrent neural networks, or you can use convolutional neural networks. I'm not fully sure if you think that that's going to be easy or not. Normally the recurrent ones, that's kind of, maybe it's easier for you to understand, because probably you have seen recurrent networks in the framework of language, mainly as a sequence of words, but you can think that audio is more just as a sequence of samples, but it's a temporal sequence. And so recurrent networks, somehow we have thought that they are super cool to encode sequences, and they are, but actually can also encode sequences with convolutional networks, which maybe it's not that popular, but that's also possible. So if you don't really know how to do it, the idea, so have you seen that? Did you have any lecture on convolutional networks for language or speech? You did? You did. Only you. Somebody else? Well, anyway, just so basic idea is that you get, instead of using 2D convolutions, you can think that your filters are only 1D, and probably that's it, right? And if you want to have memory of what happened in the past, you can always feed as input the previous prediction, and that's a way. That could be a way similar to how recurrent networks, they have their hidden state from the past. It's another way. Anyway, so the point, what I'm telling you is like these tools for convolutional neural networks, recurrent neural networks are actually also like attention layers, which are common in vision. Maybe attention and recurrent are not that common, but they can be applied to process images and video. They can be used to process audio, and to decode, same thing. There are also, you can also like decode, so then construct sequences of audio signals, both with neural networks or with convolutional neural networks. Both applies. It is true, though, that in the audio and speech communities, it is quite common that instead of just taking the raw waveform, that can be done, okay? These communities, many of them, they are very convinced that their handcrafted features, some of them, they are very valuable, and they are going to first extract some of these handcrafted features and then feed that into a neural network, okay? And they have shown that many applications that's good enough. So apart from, while in images, Alex, I think that most architectures we discuss, we feed the pixels directly into the neural networks. We don't do something before. In many audio works, first they extract things like the Mel spectrum or MFCC coefficients, whatever, but in the end they often contain spectral information, like in terms of frequencies, because they know for sure that that's very important. And they don't ask the network to learn that frequencies are important, because scientists, they are very convinced that that's important, okay? And some others, they just use raw audio and expect the network to learn whatever is important. Of course, that using extracted, handcrafted features, that helps also a network if the knowledge you extract, it's useful and it's enough, that helps the network because it doesn't need to learn so many. So that's an idea of speech encoding and decoding. That's a model which is quite popular. It was from UPC called SEGAN, in which the input is noisy voice. These are convolutions, and the output is the voice, the speech without noise. Okay, and these are all convolutions. So that would be like the encoder, and it would be the decoder. Okay. So I know that it was very brief, but I just wanted to tell you that if you have audio information, it's not that hard to fit into your neural network, okay? And there are many works there. You can start from the links I provided. Then, what if, let's assume that now you're experts, that whatever audio signal I give you, you can train your network there, you can define architecture. What can we do then? So let's look at multimodal architecture between vision and audio. So that goes from vision, so visual information to audio, and exploit this self-supervised paradigm. So one of these first works is that, so in this work, they, for each frame, they extracted the frequency information. Yeah, it's called the kilogram. That's this kind of audio features that, or representations that it's important for audio people. So, and you can compute that. So there's an algorithm that computes that. And the assumption, what they exploit here is that the sound that, so the audio track in a video, the audio and visual tracks for a video, they are correlated. They were trying to explore this. Okay. So what they did, they had a huge amount of video, so they had many frames, and they have like some audio snippet around the video frame, and they train a neural network, neural network, so that given one frame, the network should predict this kilogram, okay, whatever this audio representation. So they train that, and what they observe is that if they look, so they look at the kilograms they obtain here at the output at inference time, so at the test time, so they feed new frames, they predicted the kilogram, and then with this they clustered the kilograms based on with a clustering algorithm. And they observed now that clustering the predicted kilograms, when they look at the frames, the image frames that corresponded to the clustered kilograms, the visual frames, they also had like some common semantics. Let's say, so here you have like for each row, it would be like one of the clusters that they created with the predicted kilograms. Now you see like the first cluster, there's C, so probably that's a cluster where where the predicted audio was kind of related to the sound of waves, probably, or whatever audios or sounds you hear at the beach. The second cluster, there were like kids and babies, so probably there were in the audio track there were yelling babies. Here it seems to be some things like fun, or maybe there's music or whatever. Maybe it's a bit more strange. Here it seems to be sports. There's a ball here. Not really sure what they observed, but so they saw that there was some relation. Also, and you have seen this earlier, they observed that in the features that were learned by this neural network, some of these convolutional features, again, they had high responses to some specific semantic classes. Even though this was never trained with any label. Everything is self-supervised, okay? But they observed that high activation for some filters, they were coherent from the semantics perspective. So they had like one neuron was giving high activation for babies, and actually you can also like weakly localize the baby on the frame. Everything trained self-supervised, no manual labels. Another work they did in a similar spirit is they learned features, but in this case they created the data set of the sound and pixels of video recording of different objects that were hit with a stick, right? Yeah. So this data set is called the greatest hits data set. So in the end, so there was this Andrew Owens, the first author, who was running around MIT campus, like hitting everything he could find and recording that, and then so creating a large data set, and then again training a neural network, a commercial neural network. In this case, they introduced an LSTM on top, but in the end it was predicting the kilogram again. Okay. Then in this case, instead of doing the clustering, what he did is he looked at the kilogram, extracted features, and then he had another data set, a test data set that it was not used during training. He extracted the kilograms, the real ones, and then given one video frame, it predicted a kilogram and went to this data set. So he got a large data set and picked the kilogram, the real kilogram that was most similar to the predicted kilogram. Yeah, and then so when he found the best matching, it took the audio track from that matching kilogram, and then he added into the video. So it was sonorizing the video, okay? And it was so there was an LSTM, so there was some temporal coherence. Yeah. So now I'll show you some of the results
understand what our model's doing, we can look at the video clips in our database that it's transferring audio from. These are the audio clips whose sound features are most similar to those predicted by our model.
Okay. Yeah. So what you heard was not the first time or all the time. It was not the right. So it was not the real audio track from the video. Yeah. They were all retrieved thanks to the predicted kilograms and doing retrieval. Okay. Another nice work about audio feature learning. It's this one. It's called SoundNet. They are all from MIT, from Antonio Torralba's lab. And here what they did is, so you have your video. You feed your frames through two networks. One of them trained with ImageNet. You know that. Another one trained with Places. That's a data set, large data set also, but for locations, not for objects. Okay. The ones were trained, labeled. So given a video frame, you had like predictions of locations and objects. Then they look at the audio track. They took the raw waveform, and they define a new architecture, SoundNet architecture, convolutional one, but it's for audio, so it's 1D convolutions, not 2D. And they train this network to predict the same object or scene classes that were defined, so that defined for ImageNet and Places. In order to train it, let's say the labels, the annotations that were used, or so the predictive values, they were the ones predicted by the visual part. So this would be like what's called a teacher network. So this network that was trained in a supervised way by somebody annotating the ImageNet data set or the Places data set, it teaches the audio network what it should be doing. Do you follow that? Yeah. So I mean, somebody annotated images, and you train actually two neural networks. But if it's easier for you to think, you can think that it's only one. But you run a neural network, and then when you have a new video frame, you feed it on the upper shower. That predicts some labels for cat, dog, whatever. You feed here the raw waveform for audio, and you train this network so that at the output, if this one is telling you cats and, and the city, this network, so you train this network so that the predictions are cats and city. Yeah, so you kind of have labels for free. Well, in the end, you are kind of transferring the labels. That's why I wrote here label transfer. So you are kind of transferring the labels that you are predicting from the visual track to the audio track. Yeah. So what we are learning here are audio features. So here you see like, so this is the prediction only based on audio. So these are predictions from SoundNet, okay, from the lower network. So the lower network doesn't see any frame, any video frame, right? And you see like you have on top you have Places, predictions, and or maybe the opposite way, but I don't remember. One of them are these are objects, basically dogs. It's ImageNet, and these are Places, right? But the predictions that you see, they are based on audio only, and there was never any annotation of those videos. Yeah, the only annotations that we exploit here are the ones from ImageNet, but they are not from this data set at all. Oops, wait. Then, so the story quite quickly is that the features that they learn, they are very good, even better than many of the audio features that audio scientists had handcrafted for many years. And if you look at the features that they learned, so like the ones from the first layer, for example, you see like, so these are like 1D convolutional filters that are learned by this network. And you see that they have like their shapes. So these shapes are self-supervised learn, automatically learn. They kind of make sense, right? They seem to be matching some frequencies, which kind of makes sense. Also, if you look at the activation from a convolutional layer, you'll see what kind of similar to what we saw earlier. They saw that some of the neurons, they have high activations with correlations with, in this case, with baby talk. Some others, they have correlations with bubbles. In a similar spirit, this other work, what they do is they, so they have a convolutional neural network. That's a teacher that given as images of faces, it will look at the face expression and predict emotions. Yeah, so this one is straight manually, it's the teacher, right? But by supervising, so by exploiting the self-supervision from video, they feed sound to a voice CNN, so that's the one that you train, and this CNN, you train it to predict the emotions from the labels that come from the visual part. It's same approach as before. So in the end here, they train a network for sound that will predict emotions, but they do it by transferring somehow the labels from the visual part. Yeah. So in this case, the only notation was of faces. Somebody at some point annotated many faces for emotions, and by doing this transfer, they managed to have a network that predicts emotion from speech, from voice. Yeah. Okay, what else can we do? From vision to audio. Yeah, okay. So what if instead of learning features, we generate, we generate the audio? So that could be one classic problem. So imagine you have a video which is silent, and you want to, in this case, you predict the audio features. In this case, these features, so this problem is very specific for speech. These features, they are very well-known features for speech, so that if you predict these features, later you can synthesize speech. Speech people know exactly what they are. Okay. So actually, these authors, they have different works. So you see a video now, and they show like different works about the iteration. So there was like the first work, and then later they improve it with, they combine not only the video, but also optical flow. And well, in the end, they predict some features that will allow them to synthesize speech, from silent video. Ready? So that's the input for the.
Set wide with I7 soon. Set wide with I7 soon. Set wide with I7 soon. Set wide with I7 soon.
Okay, so of course that's quite a controlled environment, but that's something interesting, right? Okay, what about the opposite direction? What can we learn from audio to vision? From audio to vision. Okay, so that's a work we had here at UPC. We'll present next May. Here, what we did is we trained convolutional neural network. Yeah, everything is convolutional to encode speech. And so this speech is going to generate faces, and in our work, these faces, they are from, do you know this guy? Nobody? Yes? Who is this guy? Musician? A YouTuber? A musician? What is it? Both? Okay, so do you know his name or not? Okay, great. Excellent, because that's one of the first things that you can recognize the identity, so yeah. So that's a famous YouTuber called Jaime Altozano, who kindly allow us to use his data. Actually, we can generate faces from different YouTubers. Quality is not super good, but okay. Scientifically, I think it's interesting because we go from raw speech, so no frequency spectrum, so that's raw speech totally. So created a data set from 10 YouTubers, and okay, and normally it generates, most of the faces, they look realistic. Sometimes it gets confused with the identity, but also it's a bit noisy, the data set. So we do that with a GAN, Generative Adversarial Networks. I think probably you've had lectures on that. So that what a GAN is doing is actually generating different faces So yeah, so you see like here, like different faces are generated, right, for the speech coming from this YouTuber. These are like from the test set, like the average of all the faces. Maybe what is a bit better. And here what we do is we let's say we combine speech from one identity to another, right? Let's say like half. I don't know. So this Haruto Zono, I don't know who is she, but if you recognize her, you can tell me. It's okay. Another YouTuber. So let's say we combine like half speech from one and another, and then the face reconstruction is also like half. It's quite blurry because it's in between. Here there's more speech portion. So we are combining speech from two speakers, and then the face we generate is also like a mixture of them. What else we can do? We can do something that's called joint embeddings, which means that you don't try to go from one modality to another, but you try to project both modalities into the same representation. Okay, and I'll show you like why would you want to do this. So that's something we did. Yeah. So what we train a neural network that based from audio from this video that you don't see, right? So we retrieve a video whose representation matches the best on the one that we extract from audio. So we have the audio, we fit into a network that gives us a representation. Then we have a large data set of many videos, each of them with the representation, and we find the best match. Okay, so now you're listening to the audio from this video that you shouldn't see it, and then you are looking at a video whose semantics they kind of match with the ones that we extract from the audio. Yeah, maybe I should go back to the previous slide to understand what we do. So what we do is we train a neural network. So we have video. So in video you have like many pairs of sequences of images and audio tracks, right? And we train a neural network so that so we have pairs, so that if we fit the audio from one part, the representation we learn here should be the same as when we fit the video coming from this part and it's projected over here. If we train a neural network that does that when we have, let's say, one video, we take the audio and the representation it projects is exactly the same one as the one we obtain from the so one from the audio, one from the video. If we achieve that, then what we could do is we can, let's take an audio from one video, we project it to our network, we have our representation, and then we look for a video, but a video representation that matches this audio, but not from the original video, of course. Yeah. So we can go from audio to video, doing retrieval, or the opposite. We can, given this
Hola, ahora voy a hacer
video,
unas flautas de pollo. Aquí ya tengo
so
mi
given
pollo
the
cocido y deshebrado.
the feature extracted
Lo
from
cocí
this
con
video,
cebolla,
we are
cilantro
retrieving
y tomate rojo.
an audio track. So you are listening to an audio
Aquí tengo
track
mis tortillas
that
de
was
maíz.
retrieved from visual features. Yeah, and if you notice, probably most of you understand that
Vamos
this
a poner por aquí.
Spanish-speaking track, while the video, it looks that the speaker is not,
No sé si se puede estar
so
mirando.
that this cook is not speaking Spanish from her cloth,
Vamos a
but still it's
enrollar.
about cooking, right? So if you listen, you see that it's talking about cooking. So the network kind of figure
La
out
cantidad de
how to
pollo que
match
quieran ponerle
audios
adentro.
from cooking with videos from cooking. Yeah?
Esto no lleva medida.
Good. What else? A bit more impressive results are these ones where but it's the same. So it's the same spirit always. In this case, it's not that they do a joint embedding, but they are learning constructive loss. So they want, well, yeah, you can think it's a kind of a joint embedding. So they are given input video, they have end frames, the audio, and they want so they train the vision and audio network so that this is kind of similar. Okay, what I wanted to say here. Yeah, that they learn, yeah. What is nice of this work is that by training this vision and audio subnetwork, the features that they learn both from the vision and audio ones, they are very good, let's say, to later solve classification problems. Another work in this case, it's not that you are trying to make sure that the representations from vision or audio, they are exactly the same. You train a network that will predict if the matches, they correspond or not. Yeah? So you show to a network pairs of audio and video that match, so they come from the same video and they are aligned, or that don't. And then if they match, you want the network to predict yes. If they don't, you want the network to predict no. Yeah. Okay, so you train a network this way, and if you do it, in this case, notice that they are doing the log spectrogram as the input for the audio. If you do it, kind of, again, you will, and you train a network, you will see that, you will find that some, that the network will have kind of the capability of localizing, first of localizing some concepts like horizon, railway, crowd, again, kind of for free, everything. Or the opposite, you will see like, okay, and these features, they are also very good for solving some tasks, but features which are learned in a self-supervised manner. And the audio features, they are also like quite rich and they make sense. The audio features that are learned, they make sense for different semantics. And if you use them, here, for example, they compare to SoundNet. That's the one we saw earlier. So the ones we have in this work, these audio features, they perform better than SoundNet. What is also interesting is if we look at the convolutional features, in this case, you can actually have a weak location of the object that it's sounding. Okay, and that's what they show here. I think there's a video, yeah. So just by training with pairs, with pairs that match and pairs that don't match, you obtain like this kind of weak object detectors for free. Yeah, so it's telling you that this audio, it's kind of matching. It basically matches this.
I hope you guys enjoy the song, and thanks for watching, subscribing. Bye.
So he matches that this audio corresponds to violins, always in a self-supervised way. There's no manual notation ever. Okay. Fine. So there are like a few works on this direction. Here they improve it with an attention model, I think. Yeah, it's telling you like sound source localization. I think I will go back. Okay, what if we, what if instead of like raw, like general audio, we look at speech? So this is again work from people from MIT. So they had this first work in 2016, in which what they did is again they collect a data set of images, and then they recorded people describing what's in that image. Okay, so they had the speech of the description of that image. Okay, so this is no caption. Okay, there are many works that what they do is caption. I mean, they using language. So everything I'm presenting here, it's only speech, no caption at all. Okay, it's important because that's what it's really interesting. Okay, so just this image, and they ask somebody, okay, just describe whatever, and they describe, well, it's a keychain, blah blah. And then, so they had images, they have speech recordings, and then they train a neural network with pairs that match and pairs that didn't match, right? And they train a network to predict if there was a matching between the speech describing the image and the image. Yeah, that's all the training we're doing. Yeah, okay. I know that here there is no video because it's just still image, but I think it's useful still that I tell you. Then what did they observe? So they observed that. So imagine you have this image, and you have here this would be like the speech. So the audio, the speech signal, the spectrogram, and here you have written like what was the word that was pronounced, like from here to here, like this part, it was pronouncing the word field. Yeah? Fine, do you understand the figure? Then, what is interesting is like this graph. So this graph, it's telling you, it's plotting the similarity score that the network is predicting. Yeah? So what we observe that the highest similarity, so the highest similarity score is achieved with the word grassy, okay? With the phonemes grassy, which, okay, it's kind of pretty good, right? So it's this word, so it seems quite relevant and representative for this image. Yeah. While other words like, don't know, okay, maybe rising, it's not similarity at all, right? Large, okay, maybe it kind of makes sense. They kind of show that the network was kind of had the capability of finding correlations between the phonemes and the visual contents in training in a self-supervised way. Okay, then that was a work from 2016, and then last autumn, like they did this work with some students from UPC, so the Yarragazens and the DXuris, they were originally from here actually, and they went one step further, and they did kind of something similar to what we saw earlier. So they, instead of having a similarity score, now they look at the convolutional activations, the spatial activations, and they observe what part of the image was being attended throughout the speech, throughout the spoken words. So what you will see now, so again, you are comparing an image with audio, and I know that this is not video, but I guess probably the next work, the rest will be about video. So you have the image. Over here you will have the speech, and they plotted like the activations on different parts. Yeah. So now I'll show you the video, and I must tell you that the video. So I think that the visualization is not super well synchronized with the audio you will listen. But that's the problem is in the recording of the talk. Okay, because you'll see that it tells when you listen grass, you will see that the grass, or I don't know, whatever, or lighthouse, the lighthouse is not on. But that's because there's a delay in the recording of the talk. Yeah. If you go to the website, you can see like something better synchronized. But it gives you the idea. So first, this is kind of the results you see in the paper. You will see that in these images, when they feed the spoken word woman, they had like high activations in these areas, okay, which kind of correspond to the location of woman. Now let's watch the video.
So at the start of training, our networks don't know very much, and so you wouldn't expect the match maps to really give you any sort of valuable insight into what's going on. In fact, they start out quite diffuse because every piece of the audio, kind of just matches every region of the image approximately equally. But as training goes on, what you're going to see is actually we converge to an alignment that seems to be relatively stable. So after you've trained for long enough, you see these bubbles in the density start to appear, which seem to say that, this region on the left, that's capturing the girl in the blue dress, seems to really resonate with that first section of the spectrogram down there, whatever that may be. So let's take a closer look at what these match maps are actually telling us. So I'm going to show you a series of videos where we've taken the match map and we've actually then used it to modulate the alpha channel over the image, and we're going to play it through time so that it's synchronized with the audio. So basically you're going to see the image light up at a point in time wherever the network thinks it's being described.
This is a photo of a girl standing in front of a lighthouse. The little girl is wearing a blue print dress. She has blonde hair and blue eyes. The lighthouse in the background is white with a red roof.
Here in this picture, there's some skiers going up a mountain.
Large brick castle is in the distance and is surrounded by bushes.
Here we see a stretch of grass and a small road leading up to a very old ancient ruin.
A view of a very tall mountain or volcano with snow on the top, with a lush green field with red flowers in it.
Okay, probably that's enough by now. So you see that's kind of in the direction that we were talking the other way, like how humans learn. So we understand language before we learn to write and read, right? So it kind of makes sense that networks should be able to understand a speech without writing or reading. Then finally, like the most exotic architecture, what if we have like multiple inputs? and one single output. So here we have like as input like speech and vision, and the output is going to be something on speech. So this is the problem of speech separation. So you see, I think I'll go straight to the examples because we don't have much time. But the idea again is always like trying to have correlations between the spatial location and the audio.
How do you think that's fair?
Aaron, let me say the following.
Senator,
let me give you the last
stories. I will tell you there are emotional stories on both sides of the decision.
Tom, if you could, calm down just a tad bit. Aaron, let me say the following. Aaron, let me say the following. Aaron, let me say the following, please. Tom, if you can calm down just a tad.
Listen, buddy, I am calm as can be. You're the only one that gets off on these tangents about me not doing my job.
So probably you get the idea of how it's kind of related to what we saw earlier. So what about the opposite? What if you want to generate pixels instead of speech? Having as input like speech and vision. So in this work, what they did is they encode, so extract some audio features. They have identity encoder, so that's an image of a face. And what they're going to do is do visual redubbing. So they are going to generate pixels that redub the face to mimic or to say what's in the audio track. Okay, it was trained like you see as convolutional layers, fully connected, nothing very fancy, so but still quite effective, I think.
Here are some pictures of people you haven't seen before. And suppose you want them to say something. Speech to vid will do this for you. Let's see this in action. We are able to speak, thanks to the speech to vid model. We will try to read some weather news.
That rain will gradually sink its way slowly southward into the far north of England, northwest Wales. Some clear skies, though, developing in Scotland. Temperatures overnight 8 to 12 degrees Celsius. But for the bulk of England and Wales, clear skies, some patchy mist and fog, and temperatures stay.
So probably you have the idea. There's some other more recent works in which they crop the mouth. So here they were like really generating the whole image here, the whole face. In this case, they crop the mouth, but still they do something similar.
Everybody should brush his teeth after meals. Everything's all right. Don't use up all the paper when you write your letter. That's right. People ought to see a doctor once a year.
Then there are other works. I will skip because I want to show the next one. So there are like, maybe you've seen this one, was called popular at some point. In this one, they don't really generate the final pixels, but they are going to use to animate leak key points. So they assume some knowledge on what they are animating. So in this case, it are lips. So what they are doing is like predicting the shape of some synthetic lips. They are predicting with the recurrent neural network, and then they do some graphics post-processing, okay? So it's not, so in the previous ones, like the output was really like, the neural network was really generating the final output. In this one, they are generating the animation of the lips.
Given this audio as input,
it's been less than a week since the deadliest mass shooting in American history.
Our method produces the following output.
It's been less than a week since the deadliest mass shooting in American history. And foremost in all of our minds has been the loss and the grief felt by the people of Orlando.
Here's the ground truth video of Obama saying the same words.
Especially our friends who are lesbian, gay, bisexual, or transgender. I visited with the families of many of the victims on Thursday, and one thing I told them is that they're not alone. The American people and people all over the world are standing with them.
Okay. So there's this other work where they do kind of, instead of animating the lips, they animate 3D meshes. It's a bit more impressive.
Probably the most important thing we need to do is to bring the country together. And one of the skills that I bring to bear.
你们真讨厌，吃饱了喝足了就坐那儿看我说话。
Somewhere over the rainbow.
Okay, so you get an idea. And that was it for the lecture. So basically ideas that by doing self-supervised learning, maybe one of the last techniques there they introduce some more knowledge, but there are many things that can be learned, and probably it's quite an exciting field, and I encourage you to explore it. If you want to explore it and you're still looking for a master thesis, we have a project here that's called Speech to Signs. The idea is to go from speech to sign language. So that's a work, yeah. So the ideas will be, there are like different, we want to tackle two problems. One of them is to generate video from sign language. There are already like some works that manage to generate video with neural networks, especially starting from skeletons that quality is kind of reasonable, so we would like to explore on this. And also, the main issue we have with going from speech to sign language is that we don't have like a large amount of parallel corpus. It means like a large data set of videos with the exact annotation for the transcription for that videos. So we want to explore, like, there are some techniques for text that they are trying to do language translation without this parallel corpus. So it just have like many sentences in, let's say, Catalan, many sentences in Spanish. I want to do a translation, but with nobody notating like this is this, right? And there are techniques that obtain some interesting results. That will be another approach. So if you're interested on these slides, just let me know. And I think that's it. We are out of time, but if you have a question.